Hey everyone, welcome back to my channel. Today we are diving into the world of digital logic and circuit design. To make our circuit more efficient and compact, we need to simplify Boolean equations, and that's where K-maps come in. In this video, I'll show you how to use this handy tool to simplify complex Boolean expressions step by step. And let's get started. Firstly, I'm Kaushik, currently a second year student at SCCE. Now let's look at the introduction part. Boolean logic is essential in digital circuit design. As circuits grow in complexity, it is important to simplify them to reduce cost and complexity. There are two common methods for Boolean simplification. They are QM method and K-map method. And the objectives are: this study presents an approach to simplify Boolean equations using K-map method aimed at beginners in digital logic design. And the key benefits are minimizing the number of terms, reducing computational cost, and optimizing the circuit design for efficiency. Now let's look into the overview of the K-map. A K-map is a graphical tool for minimizing Boolean functions. It also reduces logic circuit complexity, resulting into a smaller circuit design with fewer gates. And the example involved in these are logic operations like AND, OR, and NOT gates are used in combination to create complex Boolean expressions. These expressions can be directly converted into hardware. And the key advantages involved in these are: it offers a visual approach to optimize logic circuits, and it is often used to design the smaller circuit designs. Simplification focus. The goal is to simplify the Boolean functions using K-map and make it easy for the beginners. And the key objectives of the K-map are applying K-map to digital circuit design within up to 7 variables, and the reducing complexity, thus lowering the design and production cost. Before we jump into an example, let's quickly go over some important terms that we will pop up while we are working with the K-maps. The first one is SOP, sum of products. It is a method of simplifying Boolean expressions. This method will reduce the number of AND and OR operations to the minimum. And minterms. These are the terms on the K-map that we want to group together. And the minterm is a combination of variables that evaluates to 1. And the prime implicants. They are key grouping of minterms that allow us to reduce the Boolean expression. We don't need to remember all these terms right away, but they'll help us to understand as we go through the example. Okay, now let's dive into how K-maps actually work. Here is a 4-step process. The first one is that input the Boolean function. First, you enter the Boolean function into the K-map by assigning the variables across the rows and columns. In this case, we'll work with 4 variables A, B, C, and D. And the second step is that group of ones. Once we have the K-map filled out, we want to group adjacent ones. These groups can be made up of ones that are next to each other horizontally or vertically, but not diagonal. Grouping them, we are simplifying the Boolean expression. And the use of gray code. This part is important. Using gray code helping us to minimize the changes between the adjacent cells, making the transactions or transitions between the groups smoother. And the fourth step is that output the simplified expression. Finally, after grouping the ones, we can write the minimized Boolean expressions. This will not only make the expression shorter, but it will also mean fewer gates in the circuits. And finally, visualization. Both SOP expression and its corresponding logic circuit are displayed as results. Let's go through sample K-map and SOP expression. Consider a Boolean function with 4 variables. In a K-map, minterms are grouped together into regions of ones, resulting in a simplified SOP expression. Minimized result. The final Boolean equation is shorter and more efficient than the original. And the benefits are reduction in the number of gates needed in the circuit. If a circuit is complex, we can make it simple by using a K-map. This is the main advantages of the K-map. Now let's see how to solve the K-map. Let's do a quick example to make it clear. The step 1, draw a 4 variable K-map. We have a Boolean function with 4 variables a, b, c and d, and the minterms we'll be working on with that is 1, 3, 7, 11 and 15. Now here is the table of 4 variable K-map and fill in these minterms. So here is how it looks like after filling the K-map. And now we group the ones we can form a 4 variable map by combining a 3, 7, 11 and 15. These make a group, and these 4 ones form a block which can be simplified. The corresponding variables are b. B is always in one block, and instead of having a long and complex equation, we have reduced it to just one variable. And here is the simplified K-map equation. And the simplified SOP equation is also B, and the benefits are the original Boolean function has been simplified into just single variable b. This reduces the number of gates needed in the circuit, and it also improves the efficiency. Now let's look into the conclusion part. So as you saw, the Karnaugh maps are a more powerful tool for simplifying the Boolean expressions, especially for beginners. Whether you are dealing with 2, 4 or even 7 variables, K-map makes the whole process visual and intuitive. The big takeaway here is that K-maps helps us to reduce the circuit complexity and save our time, and also cut down the overall production cost.